Okay, so hello everyone. Good afternoon. So we're gonna start our meeting to discuss the new G-2 results from the FNAL Formulab G-2 experiment, and it's a very exciting result. I'm gonna try to give you a bit of a perspective of what's going on in this field. So first of all, let me give an introduction to what the muon magnetic moment is. So let me share with you a paper I wrote some years ago. And okay, here it is. So in quantum dynamics, we learn that any charged particle might have a dipole moment. And that dipole moment can be different from 2, can be very, very different from 2 if it's a compositive particle. But if it is an elementary particle and it's a fermion, this G should be equal to. So you can derive this equation 1. Hold on a second. Let me close. You can derive this equation 1 using the Dirac equation, where G is a gyromagnetic moment factor, gyromagnetic factor here. Q is the charge of the particle, m is the mass of the particle, and s is its spin. And mu is the dipole moment. So in other words, this equation 1 is saying that the spin and the dipole moment are related. In other words, so as you see, they are vectors. In other words, so if I can somehow know the spin of the particle, in which direction the spin is pointing to, I know in which direction the dipole moment is pointing to. As if I know the particle involved, in other words, if I know the charge and the mass, if I know the spin, I know the dipole moment. Okay? Right? So if I know G, but if I'm trying to measure is the value of G, so I'm trying to test whether this G is precisely the value predicted by the Dirac equation. The Dirac equation predicts G to be equal to, okay, that's using classical field theory, not quantum field theory. In classical field theory, G is equal to, what I'm trying to say is, if you take into account just 3 level diagrams, G should be equal to in quantum field theory, okay? And that's it. So if there are high order effects in quantum field theory, this G should be a bit different from 2, but not much different from 2, just a bit different. So okay, let's say I'm trying to test whether these G's should be equal to. If this G is different from 2, I say we have an anomalous dipole moment. Okay? So if it's equal to, there's no anomaly, so it's just magnetic dipole moment. If it's different from 2, I say it's anomalous magnetic moment. So the way they quantify this G factor is writing like this. They define a mu factor, which is G minus 2. If A is different from 0, then there is anomalous magnetic moment. Okay, that's what you do. And then if A is larger than 0, there is a positive contribution to the magnetic moment. If A is negative, there is a negative contribution to the magnetic moment. So that said, knowing quantum field theory, you know that there are loop corrections to a particle. So a particle, mu, can couple to a photon. This photon is a magnetic field, okay? Is representing a magnetic field. But this mu is traveling. But as it travels, it might radiate off a off shell gamma, which is this guy here. Let me zoom in. It might radiate off a gamma and then meets a muon, the other leg. And in other words, so if you see a muon traveling, there is no way you can determine whether this muon radiated off a gamma because you just see a muon. You don't see if the gamma left the muon and came back to the muon. You just saw the muon. There's no way you can assess whether a gamma was exchanged or a Z boson or a W or whatever. So you just see the muon traveling. So this correction to the propagation of the muon, some of these terms can give rise to a magnetic moment. Okay? It depends on how the things go. So these quantum corrections to the muon magnetic moment give rise to anomalous magnetic moment because the number is not 2, it's different from 2. But it's anomalous in the senses if the theoretical prediction from the standard model agrees with the experimental value, it's okay. So the quantum corrections to G from the standard model is equal to the reported experimental value. If there is a discrepancy between theory and experiment, I call this an anomaly. So anomalous magnetic moment is one thing. Anomalous is being different from 2, because it is different from 2 because of quantum effects. But there is a discrepancy in the anomalous magnetic moment. It's something else. So if there was no discrepancy, it's just anomalous magnetic moment. Why? Because the value should be different from 2 because of quantum effects. But if the theory and the experiment agreed, there was just an anomalous magnetic moment, and so prediction from the standard model is correct. But there's a discrepancy in the anomaly.
I have a question. It's about, go ahead just a little bit, scroll up.
Up.
I mean, for example, for the case of the mean, we know what is his mass, the bare mass, and we know the charge and we know the spin. So let's say that at least at the magnitude of the magnetic moment, we could just to know, for example, it would be 1 over the mass, basically, if the mass changed. So in this case, what we are trying to compute in quantum effects is a kind of corrections in the new mass.
No.
So
the mu mass, we know what it is. So this thing related to bare mass or just quantum corrections to the mass, for the mu is the same.
Okay, but so what?
This has nothing to do with hierarchy problem here. Nothing to higher order correction for normalization. The mu mass is the bare mass.
Yeah, but in this case, yes, I got it. But I mean, what will change in this case?
So, for instance, okay, so that goes into before equation 1. So in quantum field theory, this term dipole moment is a term that appears in front of the Lagrangian, so which has a f mu nu.
You would have a kind of additional term in this equation.
Right. Okay. So whatever, when you have a Lagrangian and you have something that couples to f mu nu, the photon, what comes in front of this, I call dipole moment.
Yeah.
So this, because it's a quantum field theory, because f mu nu is just is quantum, right? So whatever comes in front of the f mu nu is a factor which is called dipole moment. So in other words, whatever couples to a photon contributes to the dipole moment of a particle. So if you have a muon, this remember, it's a photon, so it's a magnetic field. It's not that it radiates a photon. No, it's not a real photon. That I'm traveling, a charged particle always radiates off a photon, right? This photon has nothing to do with dipole moment.
Yeah.
This photon, I'm talking, is an off-shell photon. So it's just a magnetic field, which I represent by f mu nu. So whenever there's a particle, and if there's charged particle fills this magnetic field, this has to do with dipole moment. Okay?
So in this case, our Lagrangian term would be, instead of A,
has to have a muon, and f mu nu.
Okay.
And so because of Lorentz conservation, that must be a sigma mu nu in the middle.
Okay.
And the factor, the constant factor in front, I call geomagnetic factor. It would be the coupling, so which is related to this G.
Exactly.
Okay. So But in quantum field theory, a muon does not just, it's not muon, but muon, and gamma. Because of loop corrections, there are muon, but just in this muon light, I exchange a photon, exchange a Z, a W, blah, blah, whatever. And all this will correct at the tree-level Lagrangian. Would be like if I had many terms in the Lagrangian, but I did not include them because we just write Lagrangians at tree level, and the loop correction, we just compute them. Okay. All right. So fine. Here it is. So these are the lowest order standard model corrections to A mu. Remember, A mu is this term right here. It's G minus 2 over 2. It's just a definition. Okay. That should be equivalent. It's just the definition of A mu. The anomalous magnetic moment. So you have QED corrections, like when you exchange a photon. Weak corrections when you do exchange a Z or a W boson. And you have hadronic corrections when you have quarks in the middle. So muon does not couple to quarks easily, so it has to go through something, right? You don't have muon then quarks. So you have a muon here in the left one, and you get a muon, and that goes a photon. The photon, there's a photon, and in this loop, they are all hadrons. And the hadrons' mass are not easily to compute, and this diagram is not easy to compute. This is called vacuum polarization. Okay. And this one, the letter, is the hardest one to compute. So it's very hard to compute the standard model prediction for the last diagram. Okay?
Yes.
So at this moment, it's already important to know that the standard model prediction is not solid.
So it would be, okay.
It's not solid in the sense it's solid, but it's not precise enough. Okay? So there are, we call it theoretical systematic uncertainties in the standard model calculation. Okay? That they are not easy to assess. And at this point, there are several groups have computed this diagram, and they found different results. So then it's hard to quantify precisely the standard model theoretical prediction for A mu.
But in this case, I mean, because when we talk about hadronic effects or hadronic process, we may use some different approaches. I mean, we may use, I don't know,
different renormalization stuff.
Yes. So in this case, these groups were using different approaches, or they were using the same approach?
They use different approaches, but some of them they use the same approach. They still do not get quite the same result.
It should be approximately.
It doesn't matter, yeah.
Yes.
But the critical point is not this one. I'm gonna go back to this later. Anyway, I'm just going back. So let me just go from the beginning. You derive from the Dirac equation that the spin and the dipole moment are connected. Okay. So in other words, measuring the spin, I know the dipole moment. Okay, fine. But the point is, how do I measure the spin of the muon? Okay. And look at this. The same thing I'm saying for the muon, they've done for the electron. And they match, basically. There's a very good agreement to many orders of in the algorithm that the standard model prediction matches the quantum field theory corrections. So you compute to four loop orders, and they agree with the experimental value. I mean, this is pretty fantastic. The muon dipole moment is the most precise theoretical, I would say, is one of the greatest success of quantum field theory, because you compute at very high order loop corrections. So it changes it's like say 2.11138, and then you get 2.11138. Man, and then I'm talking about the 9 after the 8 correction. So it's like, man, it's for instance, in two sense, means it's a magnificent success of the standard model in quantum field theory. And at the same time, the level of precision we acquired in quantum field theory to question the muon magnetic moment. It's like saying, look, this thing works because I'm getting many commas right. Just the last ones that I'm discussing about, you know, the very first orders of magnitude, the first digits are fine with the experiment. Okay, fine. So if I measure the spin, I know the dipole moment. And then you have this correction, which are QED and weak. They are easily calculated, and they are agree. And the problem resides in this hadronic contribution. And what is the problem? So the main problem is the following. Theoretical computations of this hadronic effect, they now today sort of agree with each other. They kind of agree. But there are two really distinguished ways of computing the last diagram. One is really computing by hand, let's say. And the second one is data-driven. So what you have here in the end, in this one, is photon producing hadrons. That's what you have. You have a photon, and a loop of hadrons. Quarks, top, B, whatever, BB bar, top bar, pions, etc. Okay. So what some experiments have done in the past was like, wow, I'm an experimentalist. I don't care how you compute this. What I'm going to do is use the PDG, the particle data group reported value, which is based on experimental data-driven results. How is data-driven? Well, I do have photon-photon collisions in accelerators. So they do this for us. So I know how much events they produce, and then I try to determine what is the cross-section of gamma, quark. Okay, is this one? Okay, that's a cross-section. So I'm gonna get this as input to plug in the number in this blue blob and see and calculate then what is the correction to G-2 for this last diagram. Does it make sense?
Yes.
Make sense? Yeah? Okay, fine. And then this experimental data-driven has been like the canonical contribution to G-2. But in the past 4 years or so, the theoretical prediction started to diverge a lot from the experimental data-driven result. And in 2018, many groups joined and formed a collaboration called Lattice something, whatever, devoted to compute that diagram. 2 collaborations, actually. And then they found a result, and the other collaboration found a similar result, which was very different from the experimental data-driven result. What? But I say, for now, why should I care? Well, you should care in the sense that the results they found was larger than the experimental data-driven result. In other words, they are increasing the standard model prediction. And when they do increase the standard model prediction, it means that between the experimental minus theory is close to 0. In other words, the anomaly was basically over. And then you say, wow, so there's no anomaly? You're saying there is no new physics? You're saying there's just a way how you compute this stuff? And there's a battle that has been going on for some years. And recently, many groups start saying, okay, this is like a trend now. So it's very important to compute this diagram precisely. And other groups started computing this result. And now we have 3 or 4 groups using lattice calculation. And all of them sort of merged the same result. And this result gives rise to a contribution which is larger than the data-driven result. So 4 independent groups getting roughly the same result, which is different from the data-driven. If you use any of these 4 results plus the weak and QED results, the standard model prediction is minus the experimental minus the standard model prediction gives rise to like 2 sigma difference. If you use the data-driven result, this experimental minus theory is close to 5 sigma. So you have a nearly discovery, and the other you have a 2 sigma statistics bump. So the conclusions are this number of 2 might not seem much, but one means a discovery, the other is just a statistical bump. So that's the debate that we still are at this moment. Okay, but that said, let me now I went to this theoretical part. Let's go discuss the experimental part of this thing. So now I'm gonna go back to some particle physics lectures. I took this one. This thing you see here. You can see the print screen, right? On the right side, the print screen from the Shaw book, Martin Shaw book of particle physics. I do know it because I've used it in the past. So what is explained is the following. So when you do have a pion, here you have a pion, and that pion decays. And how I produce a pion? Well, you have a proton impingence on a target. I break the target. From this target comes lots of stuff. One of those stuff is a pion. Pion is a meson comprised of 2 quarks. And this pion decays very fast. The main pion decay is into muons and mu neutrino. So you have a pion plus when the pion mass is close to the muon mass. In other words, as you always say, I don't even need to talk about masses here because you already know that when a particle decays, I can go to the reference frame where the particle was at rest. Anyway, a pion plus decays. When it decays, produces a muon and a neutrino. In the rest frame, a muon should go one direction, the neutrino in the opposite direction, right? Necessarily. Yes. So if I don't see the neutrino, because I can't see the neutrino, but I do see that charged particle. So when the charged particle comes, let's say a charged particle comes in this direction. Okay, I do know that the neutrino came in this direction. But I also know that the decay of a pion is mediated by a W boson. W bosons have left-handed interactions. It's a charged current, so it's left-handed. Both particles are left-handed. So if a muon comes this way, I know that the spin points precisely in that direction, in the opposite direction. In the direction of the neutrino. But in other words, comes in the opposite direction of the momentum. Okay? Knowing this, what I do is the following. So in other words, when a proton hits a target, we produce muons. And these muons will come from momentum I know, and with the spin I know. So if I know the momentum, if I know the spin, I know the dipole moment. What I do is I turn on a magnetic field and check how the coupling between the spin and the magnetic field grows. Okay? Because there is a coupling between spin and magnetic field. Okay? You even learn in statistical mechanics there is a coupling between magnetic field and spin.
I think it is. I guess.
Right? In quantum mechanics too. Right? In statistical mechanics and quantum mechanics, we see both. One is Hamiltonian, and both are Hamiltonians. You can also write down in terms of Lagrangian. Anyways, and then when a spin, a particle couples a magnetic field, experience a lot more precession. Right? It starts rotating. I think you remember in quantum mechanics we have a spin, and you have a magnetic field pointing in this direction, and then the spin starts rotating like this in terms of the momentum. And what they are capable of are measuring the frequency at which the spin processes. And then this frequency, I'm going to show you here. Hold on. Here it is. Let me just remind again. So you have a proton hits a target, produces a pion produces a muon, and the muon comes in this direction. And the spin should be in the opposite direction, right? Because the guy's left-handed, but it's just a drawing, okay? And I have a magnetic field. The magnetic field at the beginning, when it enters in the ring, the magnetic field at the FNAL Fermilab lab, G-2 experiment, the magnetic field is pointed in a perpendicular direction to the muon spin. Anyway, as the momentum of the muon changes, because it's going synchrotron motion, the momentum is changing the direction. But as the momentum changes, the spin also changes because the muon is left-handed. The spin has to point in direction opposite to the spin. But because of the magnetic field, the spin precesses. So what you have in the end is the spin trajectory is changing, and it changes not just because of the momentum of the muon, but also because of the magnetic field in which the muon is involved in. And here, this is the frequency, for instance, the frequency dependence between the spin precession here, and the synchrotron motion. So the frequency at which the muon, the spin precession depends on the magnetic field, and there is some also dependence on the electric field. So what these guys do, it's pretty amazing. They made the setup in such a way that this term right here is smaller than mu. So for instance, what they do is they tune the velocity of the muon when it enters the ring so that they can neglect the electric field component in the ring. So all the apparatus, proton hitting a target, the target produce pions, pions decay produce muons. They target the setup in such a way that when the pion decays, produces muons with certain velocity. Okay? And they try to tune this velocity. And they call this magic gamma. Here it is. And then they remove the dependence on the electric field. In other words, just knowing the magnetic field, they can determine, for instance, they know the magnetic field B because they set up the experiment. I know the charge of the particle. I know the muon mass. In other words, if I measure the frequency, I know the dipole moment. I know B, I know muon mass, I know the charge of the muon. If I measure the frequency, I measure the dipole moment. And now check out check this out. Look at the one of the old results related to G-2. Let's look at this. So the standard model prediction was in this case, and these things depends precisely on some uncertainties, right? Look at the numbers: 116,591,802. The other is 116,591,828. So it's 02 or 28. And look at this. This number here, 2 or 48 and 26, are corrections to these last two digits. These three numbers are corrections to these last two digits. Could be, for instance, 2 or 4 if you include this uncertainty, or 2 instead of being 2 could be 44 because if you include this uncertainty, or plus 26, 02 plus 26. Okay, so what I'm trying to say is the uncertainty is if you sum all these three, that's the size of the uncertainty that you're going to change in the last two digits of this value. Okay, that's the standard model prediction, 10 to minus 11. So that's why I'm saying is a correction in the digit 10 to 11 digits. Well, it's not 10 to 11 because if you multiply by 10 to minus 11, you're going to go lots of zeros. You're going to end up with, I don't know, how many relevant digits you're going to have. But the precision, anyways, is quite fantastic. And what I'm saying is, why these numbers are in parentheses? Because they have different orange. One has to do, for instance, here it is. Theory errors in parentheses account for electroweak. So see the error of electroweak. It's just 2. Lowest order hadronic is 42. See how sizable it is. And high order hadronic contribution. So if you had higher loops to that vacuum polarization, it's just going to change the final result by 26 in these last 2 digits. So the lowest order hadronic contribution, which is that gamma gamma in a blob, that's the largest error. And let me show you some table where you have the difference between the standard model and theory. I'll say this kinds of gives you how precise it is. Here it is. So the first measurement came in 1957. So the muon magnetic moment was 0. And 59 was 0.01. 61, look, is 0.01. Look at the digits that we are correcting. 65 already stayed, see? Now came from 865, let me zoom in. 859, now went to 5911. No, but 91 is already sort of correct. 9 is correct. It's 919. No, it's 920. No, it's not 920. 920.02. 923. No, it's 921. 4. So you're just changing the last digits. So this one is the very famous result. This 2004 and 2006. Because they reach a precision which is way more, way better than the previous results. And that's roughly when the anomaly came out. So when the theory and the experiment they were not in agreement, and there was a discrepancy between the muon anomalous magnetic moment. So now you can see the value is 001, 165, 921. But as you change it to the last 2 digits, then you can go to 920, 89. So those are the digits that we are talking about in this meeting. So it's not these ones, but the last ones. And that's, for me, that's something that you cannot see in any science subject whatsoever. You'll never see someone discussing 1, 2, 3, 4, 5, 6, 7, 8, the 8th digit of a measurement, and using that 8th digit to search for something new. I mean, this doesn't exist in any area of science or whatever, material science, whatever you can think of. You never discuss this. I mean, that's the excitement of field theory. Huh? Okay, that's quite amazing. Anyway, and that's the result. So for instance, at the end, that's the experimental measurement, right? So from 2004, 2006. And the difference between experiment and theory was around this value, around 280 10 to minus 11. Or if you say in the order of 10 to minus 8. So you are really assessing the 8th digit of the measurement. So you're trying to assess which digit should be in the 8th significant digit of a given measurement. So it's quite fantastic. Anyways, so that was the history before the mu G-2 experiment. So I might say that at this point, 2006, there was a discrepancy, and I mean, many papers came out at that time. I was not even in physics. And then many of the members of the BNL collaboration went to Fermilab, and they brought the ring to Fermilab, the whole ring to Fermilab. And they built the same experiment that was at BNL at Fermilab. I mean, they used the ring. The experiment is updated, the electronic system, blah, 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 and so on. And let me see if I can even show you on YouTube. Let me open a different one. So you can see how fantastic it is. This is quite amazing. Mu g minus 2 mu what mu g minus 2 arrival formula. You see, here it is. Ten years ago. Hmm. Look at this. I should say that this area is like the Chicago area. So this guy is stop the traffic in one of the highways of Chicago. Man, that's like I can't imagine driving this car in particle physics, huh? Mm. No. So we are talking about a country where people stop to take pictures of particle physics experiment. Hmm? So I think I told you this story before, but when I went to a pharmacy to get a medication, to buy medication, then the girl, the attendant, saw me with the Formula badge, and she said, "Ah, you at Formula?" I was, "Yes, I am." Wow, you guys are amazing. I was like, what? Like, a girl from pharmacy thinks I'm a physicist and I'm amazing? Like, man, I thought I was, in a different planet. Anyways, so now let's go back to the what really matters. And okay, so now you learn how you can produce muons and how we can sort of measure them. Let's say I give a scratch of how we can really measure this thing. And now let's go to the science talk from Fermat. So this guy is just discussing the precession that I just was talking to you. So let me now speak a little bit. So I do say that's how I say it's one of the most important messages that I have to give to get across to all of you is that despite being a theorist, you do have to listen to those experimental talks because you learn sort of the details of how things are measured. And if you want to propose ever a new technique of how to discover things, you have to learn how these guys think. And so you really learn how this. For instance, for theory size, I say I have a detector which is perfect. There is nothing. I need this a superconductor that can measure whatever. And that's the theory. But when you do want to propose something that a new technique, you have to come up with something like conceivable, something that's really is feasible to put in practice, but it's conceivable in the sense that in practice you can really get this done. Right? So let me just show you the main results for us. Let's say, let me go back there. Here it is. Here it is. Here it is. So in that point, so that's the BNL measurement. That's the one I showed you before, from 2006. So this blob here is the central value, and the central value of the last G-2 result reported by the FNAL. FNAL is an abbreviation for FERMLAB. Was this value right here, which was below. So what I'm saying is, what before was saying is that, look, remember, give the perspective, understand the perspective. Before FNAL G-2 experiment, what they had was theories disagreeing with each other, saying, look, my data-driven results is this, and your latest results are this. So the last results decrease the significance of the signal, and the experimental data-driven results increase the significance of the new physics signal. So that was this debate. And then several groups combined agree with the result where the hadronic contribution gives rise to a much less significance in the delta mu. So the delta mu from the lattice is 2.2 sigma. Using data-driven is like 4 sigma. There was a discussion. So many people said, look, maybe the data-driven results not the right way to do it because it's data-driven. So we are talking about high energy gamma events, and now trying to use these high gamma events to do something which is low energy gamma events. It's a gamma rating, off-shell gamma from a muon lag. It's not the same energy of a gamma at a high energy. So maybe the way you're doing this thing is not correct. And they go, but it's data-driven. And you guys don't know so precisely how to compute these lattice calculations. So that was a debate. And then came the first FNAL result showing that the central value was actually smaller. I said, see, there is no new signal. The theory is increasing the value, and the experimental value even decreased further the significance because the central value was in blue, and the central value of the red is below, right? It's below 21. Mm-hmm. But look the size of the error bars. So statistically speaking, this central value is still consistent with the red measurement because all this band is okay, right? That was the status. And so far, he was just giving a historical perspective. And he shows on live, there's one guy, like 2 people, the director is someone who carried out the analysis, who knows the final result. And they open live the envelopes saying what the new value is. So everybody can see. Oh, are you ready? Once I do recognize where he is, he's at the FermLab auditorium, which is huge. So these talks are just for like these moments where the Higgs even the Higgs discovery when it was announced was not at this same place, was not there. So this is at the FermLab auditorium. Well, here it is. So at the end of the day, so if you include run 1, you get the very first one here. The run 2, you get this one, and the combined analysis using statistics of both experiments, of both measurements, you get an error bar which is a bit smaller, but much smaller than the blue one. And then that's the road average, which is 20.5. So now look at this number. 0.00011659. Now let's just go back there and see the value. 0.000.11659. See, we are getting the same result as before. And now what we are changing is that's 2, 1. This is 2, 0. What this guy is showing is that should be 2, 0, and now the next digit is 5. If you look at this one, it's 2, 0, and now instead of being 8, is 5. Okay? So this is the number that I'm changing. When you look at here, seems like, wow, this thing is very different from that one. But these guys are changed like the comma in like from 8 to 5. So that's what it is. But the main difference is the error bar. That's the greatest thing that is. Because he shows this amount of prediction. Yeah. So the standard model prediction is there. And that's where the experimental is. Try to, in some way, given the error bar, there is no way you're going to go to the green region, even despite the size of the uncertainty of the green region, which is here. You simply cannot go from here to there.
What exactly means this kind of shallow?
Shaded?
Yeah,
the size of the error bar.
No, I mean it's going to
from 17.5 up to 19.
But somehow it is becoming, how can I say, fainting. Yes.
I mean, just must be a
Like
factor from the plot or something from the screen.
maybe it's just.
Yeah, it's maybe just because of his screen, but there's nothing. So it's like to say 17.6, whatever this was,
Anyway,
is around 19-ish. So you need something that's new physics that jumps from this value to this value. And given the discrepancy between this one and this one, the difference is about 5 sigma, 5.1 sigma. Okay, between these two. But again, these guys are using this result, which is not the same of the results reported by these lattice group calculations. Okay, it's not the same. It is 5 sigma. It is 5.1. Man, the point is, if this is not going to be resolved anytime soon, but in some years from now, if it is resolved, we have found a new evidence for physics beyond the standard model. Period. And we are living to see this, you know. So in the beginning, one of those guys was when the ring was passing behind him, and he was discussing, and he said, "This is something that we see in a lifetime." Yes. You know, so you see an experiment being built that these guys discussed in 1980 something, and now in 2000 and something, these guys are seeing the experiment being built. Would be something like this dark sector being built, and we are 60 years old and seeing this thing being built. Man, this is like something that money cannot pay for. Yeah, it's like it's a dream coming true. Oh, here it is. So here it is. So now that's the key point, so we can finalize. So the standard model lattice calculation, that's the one that I told you that does not agree with this one. So you can see the yellowish does not agree with the greenish-ish central value at all. But it's still, you cannot go from the yellowish region to the road average point. Okay? You simply cannot. Fine. And the point is, obviously, the significance from going to this purple one to the green one is 5.1 sigma. But going from this central value here to the purple one, it must be, 2 sigma and something. Okay? So depends. So the significance is 5 sigma if you consider these central values, standard model prediction. It is 2 point something sigma if you assume this lattice calculation. Okay?
So this lattice HVP means
hadron vacuum polarization.
Okay. So in this case, they are using lattice KCD or something like this. That's the difference. The yellow, yes, they're using.
And for instance, this one I'm not aware of. I don't know what it is precisely. So it's just saying that E plus E minus from hadron vacuum polarization using only CMD3. I don't know, maybe it's a detector. CMD3 data, right? Must be some detector below 1 GeV because it's low energy. So he's saying that this value here is here, which is quite different from this one. See?
Yes.
So the blue and the green are very, very different. And he also, this blue is way more in agreement with the yellow one than with the green one. The method seems to be different, but they are disagreeing with each other, right? By a lot. So that's why I'm saying that this battle is far from over. Anyway, so let me just like this, and just to conclude the talk today is to show you that this the same way here when I showed you before that we had the weak and hadronic corrections to G-2. Here it is. Where are the diagrams? Here, there it is. So what it means is, if you have a new physics model that does have a Z prime instead of a Z boson, it will contribute to G-2, period. Well, as long as it couples to muons, right? Muons. Because that's the diagram that will be, well, if it does couple to quarks only, if it's just to quarks, is non-trivial. It would be higher order corrections. But if it does couple, if I have a charged particle will always contribute in this diagram.
Okay, I think I got it. Okay, we have a theoretical calculation that gives the distance from the experimental, like 2 sigma, something like this. The other is 5 sigma.
Mm-hmm.
But anyways, it seems that we need new physics, not just to understand, not just to understand the hadronic process, but new physics.
Yeah, because the hadronic process, we don't want to enter into this game, right? They say, look, I don't want to enter into this game of hadronic lattice calculations. Yes. What I'm saying is, let's assume, I have to assume something. Let's assume that you guys are right, whatever you guys are. There is still a discrepancy.
So you assume, okay.
What is the new physics fields I need to introduce into the standard model? When I compute the G-D AMU of those new fields, and then I add with the standard model theoretical prediction, which now the value matches the experimental result. And has to be positive, okay? Because there's a positive difference. If we were different, then there are particles that give rise to a negative contribution to G-. It's not necessarily positive. It can be negative too. So, for instance, there are particles which have just, for instance, pseudo-scalar couplings will give rise to negative contributions. Charge fermions, charge scalars, negative contributions to G-2. So if G-2 is correct, cannot be charged particles, basically. Okay. It cannot be charged fields. Charged scalar fields.
At least not only them.
Yeah, not only them. So they would not be the answer. Okay. So, but a Z prime E does. But the point is, it's not easy. Well, it's easy to explain the discrepancy. What is not easy is to explain the discrepancy and show why we haven't seen any sign of this field anywhere else. So, yeah, the bounds. So why we haven't seen this Z prime at the LHC? Why we haven't seen the Z prime at the lab? It's coupling to muons. So why shouldn't it couple to muons and not coupling to electrons? And we have data from lab, which didn't see any Z prime. So
at the same time, you need something which has a relatively large cross section, but at the same time, it cannot be observed, has not been observed so far in detectors.
So the coupling stimulus has to be something sizable enough to explain the anomaly, but not sizable enough with everything else, otherwise we would have seen it already. And it's non-trivial. So the most popular explanation to G-2 today is when you extend the standard model with a gauge symmetry with L mu minus L tau. So muon and lepton numbers, muon and tau numbers, flavor numbers are gauged. So in this mu minus tau symmetry was not really a trend. But when the G-2 result came from FNAL and said, wow, so people were trying to come up with models to explain it, and it was really hard because of the bounds. And then someone, Werner Hodde-Johann from Max Planck, had written a paper proposing this mu-tau symmetry, but not for a G-2, but for neutrino mass models, oscillations, blah, blah, blah. But then with these new results came out, people said, mu-tau, because mu and tau does not couple to electrons. So it does not have the bounds from lab. So it's just to mu and tau. So it does not couple to quarks. There is no LHC bounds. That's perfect. Yes. And then it's mu minus tau, and then all the extensions, including G-tau, you can imagine, were proposed. Mm-hmm. And that has been the solution for explaining G-2. But sorry, I took too long already, so I'm gonna end up the live. And thank you all for listening to us so much, and have a nice weekend, you all. Bye.